Hello, welcome to another lecture, and this one is on earthquakes. This is part one, so it's part one of two lectures. So in this one, we're going to be learning all about what earthquakes are and how the science behind them, and how we locate them on Earth when they occur, and how we measure them. There's different ways to measure their strength. So this opening slide is from the Haitian earthquake that struck the country of Haiti back in 2010. Or was it 2011? I think 2010. And it wreaked havoc on that city. This is the capital city of Haiti, Port-au-Prince, and essentially the whole city collapsed. So earthquakes is this emission of energy, as we'll see, when there's movement along a fault line, this fracture you get in the Earth's surface in crustal rocks. And when you have movement in opposing directions along a fault line, tension builds up and builds up and builds up, and finally friction's overcome, and you have slippage or rupture along that fault line, what's called displacement. And when that occurs, huge amounts of energy are released and radiate in all directions from that point. And as that energy transmits through the Earth, it transmits as what are called seismic waves, and they at the surface cause ground shaking, movement of the ground, and that's what causes the death and the destruction of buildings, etc. It's from this ground shaking. Here, this opening photo, as I said, is from the country of Haiti. The poorest country actually in the Americas, North or South America, and back in 2010, a major earthquake, 7.0 on the earthquake scale, on the magnitude scale, occurred, and the whole city collapsed, and 160,000 plus people lost their lives. Huge, catastrophic natural disaster. So it shows, the potential for earthquakes to wreak huge amounts of destruction and sort of dire consequences, essentially. And so the subject of studying earthquake by scientists is very important, because it's our objective really to be able to kind of maybe hopefully forecast earthquakes, or what to do to reduce or mitigate the risks of building collapse. So as we'll see in part two of this series of lectures, we look at what sort of things we can do to mitigate that risk. For example, building buildings to a higher grade, higher building codes. Here in Port-au-Prince in Haiti, there were no building codes really as such to prevent building collapse after ground shaking, and everything collapsed. Here you can see 1, 2, 3, 4, 5-story building, what was a 5-story building, just like a pack of cards collapsed, and people inside had very little chance, unfortunately, to survive that. We'll see other countries, though, have very high building codes. Places like the United States, in California specifically, where on the West Coast, where earthquakes are prone, or more likely. Other countries like Japan have very high building codes. So those buildings are designed so they can withstand ground shaking, unlike in Haiti, and save countless thousands of lives. It's worth bearing in mind, by the way, that thousands of earthquakes happen on Earth every day, but many of them are only felt just very slightly by people in the vicinity of them, and they're very low in energy, and they don't cause or very little destruction, so it never gets onto our kind of our news channels. All right, let's plow on. What we're going to cover in this part one is what is an earthquake, and then we're going to ask about or learn about the study of earthquake waves. It's called seismology, so it's to do with seismic waves, these waves of energy which radiate from an earthquake. We're going to learn how to locate an earthquake. The diagram at the back of this slide actually is linked to that. So how do we locate an earthquake when it occurs? And we'll find out any earthquake anywhere on the planet, there's a system where we can measure these seismic waves, and calculate where the location of that earthquake. And then we'll talk about how we measure the size of earthquakes. We can measure it in two different scales, something called the intensity scale, which is basically how much destruction occurs locally to buildings especially, and more scientific scale, the magnitude scale, what used to be called the Richter scale, but now it's called the moment magnitude scale. And this directly measures the amount of energy emitted from an earthquake. All right, so there's a clip here. I won't play this now, but please stop the video and do follow this link to a YouTube. It's only two minutes long or so, but it's a nice, very basic but very good introduction to the subject of earthquakes. Kind of earthquakes 101, if you will. Okay, so what is an earthquake? To define one sort of briefly, where an earthquake is a vibration of earth produced by the rapid release of energy. So this energy release radiates in all directions from its source, and the source is a crucial term called the focus. It's also called the hypocenter in some sources, but let's just call it the focus today. And the energy as released from that point is in the form of waves or seismic waves. So here in this diagram illustrates this. So earthquakes, as I mentioned, they occur when there's displacement or rupture along a fault line, these fractures in the Earth's surface. And as we'll find out, faults are created either due to compression of the Earth's crust, going back to plate tectonics, when plates are coming together, or extension of the Earth's crust, when there's rifting and there's extension of the Earth's crust, again due to plate tectonics. And that will cause the Earth's surface, the Earth's brittle upper part of the crust, to fracture, either to slide over each other from compression or to kind of extend, and you get these fault lines. So when that occurs, you have an earthquake occur. So remember what I was saying earlier, when you have one bit of rock and another bit of rock along a fault line, and they move in opposing directions, they build up stress, builds up, and finally that they're stuck together due to friction essentially, and finally that friction is overcome and they move, and displacement, and that's when you have a release of energy. And as we'll see, it's actually the rocks kind of strain, and we'll go into that point a little bit more detail soon. So the release of energy radiates out in Earth in waves called seismic waves from the focus. And a key point here is the epicenter. You may not have heard of the focus, also called the hypocenter sometimes. The epicenter, I'm sure you have heard of that word, that term. It's news, you know, when earthquakes occur on the news, they often say where the epicenter is, and that's what it means. It's a description of the location. So it says at the bottom here, the focus is the zone within the Earth where the initial displacement occurs. The epicenter is the surface location directly above the focus. So it's a location on the Earth's surface directly above the focus. So you can put it on a map, essentially, to show people where the earthquake is centered on. But the energy itself is released from the actual focus on the fault line underground. Sometimes it's shallow, sometimes it can be actually quite deep below, near to subduction zones. So earthquakes, as I said, occur along these fault lines. Movements of faults are associated with movements that produce earthquakes are usually associated with large fractures in the Earth's crust called faults. Most of the motion along faults can be explained, as I said, by plate tectonics, either by compression or by extension, or sometimes what are called transform faults, thinking back to plate tectonics, such as the famous one in the United States, if you can remember, the San Andreas fault. And so here we have a transform fault plate boundary, and there's horizontal plate movement in opposing, opposing directions. So the North American plate is moving one way, and the Pacific plate is moving the opposite way, in this case for the San Andreas. It's something called shear. It's shearing in opposite directions. So to show you some examples here from crustal rocks being extended, the Earth's crust, and here you can see how fault fractures open up, and again from extension, and here on the right from compression. and here the crustal rocks are compressed. So to show those images again, the next couple of slides. So first of all, faults are fractures. Yep, along which appreciable displacement has taken place. They're classified different faults, so we're going to talk about the different types of faults by their relative movement. If it's a vertical displacement, either up or down of one side of the fault plane, they're called dip-slip faults. So the movement is parallel to the dip of the fault. The dip of the fault, if you have a flat surface underground, which is a fault, essentially, a crack in your surface, is usually always inclined often. The dip is simply the angle pointing down. That's the angle dip. So it might be 45 degrees, it might be 20 degrees, it might be 70 degrees, but that's the dip angle and that's the direction. So the movement is parallel to the dip. It's either a block on this side of the fault plane moving down, or on this side, the below moving up, etc., as we'll see in diagrams. So these are dip-slip faults, and there's two main types. There's normal faults and reverse, and the extreme of a reverse acute angle is called a thrust fault. So here shows normal faults at the top and reverse faults at the bottom. So here at the top you have extension of the Earth's crust, where you say continental rifting areas, which occur, say, in East Africa, but also parts of the United States, in the Basin and Range region of the southwest of the United States, as an example. So here you have these normal faults opening up from extension, and note there's some terms here, some quite key terms. The top side of the fault plane, so on top, the rock above the fault plane, is called the hanging wall block, and the rocks below the fault plane, this area, are called the footwall block. And you can describe simply in words a normal fault by saying the hanging wall block moves down relative to the footwall block. And that would describe a normal fault. The hanging wall is displaced down relative to the footwall block. It's associated with these mountains called fault block mountains as well. The reverse fault, it's the other way around. Here it's compression. So the Earth, the original Earth is like this, flat, but it's compressive. So basically one bit slides over the other to shorten the Earth's crust. And you have these along these fracture planes, these faults. So here the hanging wall moves up relative to, instead of moving down, it moves up the hanging wall relative to the footwall. If the dip is less than 45 degrees, so let's say 45 degrees if it's more of a shallow angle, we have what's called a thrust fault, a type of reverse fault, specifically called a thrust fault. Just going back to just illustrate, I think, a little bit of historical note, which I find interesting, where these terms hanging wall and footwall come from. They actually come from old mining terminology. We're talking a long time ago, sort of centuries old terminology. So the footwall, here you can see on the diagrams now, there's a miner. Often these along faults you get valuable minerals forming, so you mine out this fault to extract and mine these precious metals or certain minerals which can be mined economically. So the footwall block below the fault plane, the miner would stand here. That would be, it might be inclined, but that's where his feet would be on. The hanging wall block above the fault plane, that's where he could literally hang a lantern on, which I think is kind of cool to think about. But that's where the terms come from. So that's where they're derived from. That historical background there. Thrust fault, like I say, when it's more, the angle is less than 45 degrees, maybe 20-degree angle. So here it slides across the footwall block here, the hanging wall block does, and you have what's called a thrust fault. To show you just a couple of photos of what these things look like, in an outcrop on the left. So here you have the ground surface at the top of this photograph on the left. There's grass and it looks like a desert environment. But here you can see a fracture running down a cliff line, and here you can see the exposed rocks in that cliff. So you can see these layers of sedimentary rock, different types, darker rock and a white rock. Let's call it the white rock limestone. So here you can see there's a thick limestone on the right-hand side of this fault plane, and three beds. And if you look on the left-hand side of the fault plane, the identical, thicknesses of those beds outcrop here at a lower point. So what's happened? You've had an earthquake and displacement down that fault plane. So you've had movement down the fault plane on the left-hand side, displacement. So here you're getting extension. And if you can remember what they're called, that means this must be a normal fault. Compression is a reverse fault. Extension is a normal fault. Here on the right, just an image from one of the deserts in the southwest United States, and here you can see there's been a quite recent earthquake, and you can see vertical displacement upwards on the right hand, so you can see the fault line, and there's a person there for scale where it's moved up maybe about 1.5 meters, maybe 5 or 6 feet. Okay, so they're the two types of dip-slip faults, the normal and the reverse. Then there's also strike-slip faults. And so there's your kind of dip angle in kind of structural geology. That's your dip, the angle going down a slope or a fault plane. The strike is kind of the horizontal line. So if I was to measure a strike, there's your dip angle. The strike is, if I put this pen, if you can see in the photo here, that's your horizontal line, so it's that direction, north or south, whatever the compass direction is. That's your strike. When we take measurements of beds of rock in the earth, that's what geologists do. They measure the strike and they measure the dip, the orientation of that bed, or in this case a fault. So the strike is movement in the horizontal direction rather than the up or down. So dominant displacement is horizontal, or what's called shear, and parallel to the strike of the fault. And here you can see at the bottom here. So there's two types of strike-slip fault. There's a right lateral and a left lateral. And it's all to do, you have to imagine yourself sort of standing on one side of the fault. So say if you're stood here where you can see the red dot on the near side of this diagram at the bottom, and you look across the fault plane, across the fault line, what happens to the movement, this displacement from an earthquake, what happens to the other side of the fault line? Is the rocks over there, are they moving to the right? That would be a right lateral fault. Or are they moving to the left, which is the left lateral strike-slip fault? So here, right lateral, as you face a fault, the opposite side of the fault moves to the right. Left lateral, as you face a fault, the opposite side of the fault moves to the left. So kind of think about that. Imagine you stood on the near side of this fault. You're looking across the far side. What happens? And that's how you define these things. So it's a right lateral strike-slip fault or a left lateral strike-slip fault. So this one is, it doesn't label it here. It says strike-slip fault, but it doesn't say which one. Well, you're looking across. It's moving to the right on the other side. So therefore, it's a right lateral fault. If you were, by the way, to jump across that fault line, look in the other direction, and imagine you're kind of a person just over there looking towards us now, the same thing would happen. So it would always be a right lateral fault, whichever direction you're looking at that. There it is in close up, and you can see the term shear as well. Famous one in the US is, or in the world, sorry, really, is the San Andreas fault. And this is not just a normal sort of fault where, it may go down a few hundred meters, maybe a kilometer, but this is right through the Earth's crust. It's what's called a transform fault, a plate boundary, indeed. But it's also got other faults associated with the San Andreas fault, especially something called the Hayward fault, which runs through the Oakland side of San Francisco Bay, for example. And all of these are quite active. They have earthquakes occurring along not just the San Andreas, but also these other fault lines mapped out here in California. And like I say, the San Andreas fault and the Hayward fault are all they're strike-slip faults, so there's horizontal movement along them. Here on the bottom left, you can see a photograph of a flyover of the San Andreas fault and a drawing of what's going on. And you can see on the top part of it, the North American plate is moving to the right in this case of this field of view, and the Pacific plate in the near to us is moving to the left. And there's a series of earthquakes at home, so you can see a stream here, and there's a big right angle. It's called a dog leg. Goes down, across, and back down again. It wouldn't normally, that stream probably wouldn't have normally been like that. It would have just been a nice flow all the way down. What's happened, there's been a fault or probably actually a series of earthquakes along the San Andreas here, and that's displaced the stream line by, it's hard to get a sense of scale here, maybe, you know, a couple of 100 feet, maybe 100 meters or so. Okay, here's another flyover of the San Andreas Fault. You can see this from this is from a plane, but you can see it from space. You know, it's a huge fracture in the Earth's surface, the San Andreas. Here's the image of the San Andreas Fault. Sorry, it's what caused an earthquake associated with the San Andreas, which runs through San Francisco, and the famous earthquake of 1906. And here you can see the city of San Francisco ablaze. So what happened here was, yes, you had some ground shaking and building collapse, and that caused a lot of destruction and fatalities, unfortunately. But also there were great fires consumed the city at the time. They'd just been put in kind of state of the art back in 1906. Gas lines, you know, gas pipes, gas lines had just been put in for gas lighting, etc. in the city. You can see a gas light there on the street side there on the left there. And unfortunately, and this still happens today, like you can see in the photograph on the right, those gas lines are ruptured and they can then ignite and cause fires, which can cause an awful lot of destruction from this secondary hazard essentially associated with the earthquake. Here's the destruction which I talked about earlier, so I won't repeat myself too much, but here it is, the Haitian earthquake of 2010, 7.0 on what we call the magnitude scale, the scale of energy released, occurred in the country of Haiti, the capital city Port-au-Prince, back in 2010. There was a smaller earthquake back in, or still actually quite a big earthquake in 2021. But that was the epicenter for that earthquake was quite a way away from Port-au-Prince. It was along to the western part of the island, so less populated, but still caused a few hundred deaths and fatalities. But this one back in 2010, the epicenter was right near, unfortunately, right near the capital city, and hence the huge loss of life at the time. But you can see it was mainly due to very poor construction methods. Like I say, it's got a very low GDP, so they don't have the resources or the funds essentially to build to a high degree of earthquake-proof design, if you will. So let's go back. Next subject is the very briefly, just really on this slide, the actual what happens during an earthquake, and this kind of diagram takes you through what's actually going on in the ground. It's something called the theory of elastic rebound. It's from a physicist, a geophysicist, came up with this theory. He worked at Johns Hopkins University, if I remember right, in Baltimore, in Maryland, the United States. But here, so I'll take you through it. So here you have your original starting position on the top left, but you have a fault, pre-existing fracture in the Earth's surface running through. You have a fence line, so it helps you see what happens when there is an earthquake. So on each side of that fault, you have two blocks of Earth, if you will. So here we have what's called deformation. So here we have movement. So let's call it the Pacific plate on the right, or sorry, the North American plate on the right, and the Pacific plate on the left. And there's movement of the North American plate down to the right, and there's movement up of the left-hand side of the fault. Let's call it the Pacific plate. At first, the rocks don't just suddenly, you know, because friction's keeping them together. They don't just straight away slip along that, displace along the fault line. What happens? You have deformation or strain occurring within the rock. So they're strained and they deform, they bend, if you will, due to that huge forces on each side. So you have this deformation phase. When that happens, you build up energy. A storage of elastic energy is built up on each side as you're stretching them out. Almost like you're stretching an elastic band, if you will. You're starting to store energy. On the right, finally, along that fault line, friction's overcome. The amount of strain is too great, and then you have movement along the fault plane, which releases energy. But the most amount of energy is emitted from those two deformed blocks of Earth, coming back to their original point. So they're rebounding to their original undeformed shape, and that's when you have a release of energy. So here, see rupture or slippage and release of energy when frictional resistance holding the rocks together is overcome. Remember, rocks aren't just a nice smooth plane often. You think of saw teeth along a saw, a jagged saw. So that's what's gripping them together each side of this fault line. So here on D, it says rocks rebound to their original undeformed shape, and it's that elastic rebound which releases the energy and gives you the earthquake. That's the key. To illustrate that, here on the top left, you're building up energy. Here you're stretching an elastic band, you're building up this energy, you're applying strain, and elastic energy is being built up. You release it, and you release the energy when you do that. You can do the same if you actually let an elastic band fly across the room. Here on the right, I've done this kind of in the lab as an illustration to students. And here you have a heavy weight on the flat bench surface, table surface, and you have a spring. You pull the spring. Eventually, at first, the spring, your stress is building up as you pull that, extend that spring. But the block, because of its weight, it still stays stationary. Eventually, though, you will have movement. The stress is so great that you'll be able to drag that block along the table. Imagine the table being a fault surface, and you have slippage, in other words. And you can do that. So you go for a cycle: building up stress, earthquake; building up stress, and earthquake. So you often get this a cycle of stress build up, and then finally release and elastic rebound, and then stress building up again along a fault plane. So you start to have earthquakes every few decades, every century, when this occurs. Here you can see an earthquake has occurred along a fault line running through this orchard. I think the orange trees, and this is a picture from California, so it's again near the San Andreas. And you can see an older picture showing what's going on. Here's displacement of fence line by about 2 meters or so. And you can see here that, but the olive grove, you can see all these rows of trees are kind of offset. So I don't think the farmer would originally have, planted those trees like that, unless, he's had one too many the night before. But so they've been moved along a fault line. So there's been an earthquake, and a fault runs through that farmer's field. Sometimes earthquakes don't occur just in one kind of big hit. Sometimes you can have gradual movement, just a small amount of movement along a fault line, and then it's called a term called tectonic creep or fault creep. So there's gradual movement, such that earthquakes are not felt, can produce slow earthquakes, and this also called fault creep. They can slowly damage roads. You can get cracks along roads. You can see the evidence of them on the surface in structures, sidewalks, in paths, and building foundations. Okay. What is an earthquake? So before you get that main earthquake, often you can get smaller movements, displacements along a fault line called foreshocks. Then after the main displacement, you also get slight adjustments taking place on each side of the fault line, and these are called aftershocks. And sometimes these things, aftershocks and foreshocks, can actually be significant earthquakes in themselves. So small earthquakes called foreshocks often precede a major earthquake by days sometimes, or in some cases as much as years, but usually sort of days or weeks. And sometimes they give you a clue something big is going to happen, but also you don't know if this foreshock is the final event or there's more to come. Adjustments follow a major earthquake often generate smaller earthquakes called aftershocks, and these will be now smaller in size. And the key here, because of the potential for aftershocks, if you happen to be, you live through an earthquake, you're inside a building, the building hasn't collapsed. The key is, if you're in the ground floor, as we'll see in part 2 of these lectures, is to try and get out, but if not, to shelter under a sturdy table or something or such like. But anyway, after the main event, then you evacuate the building. If you were inside, do not go back inside that building. There may well be, and there probably will be, aftershocks, and those smaller earthquakes might be just enough to to make that building then collapse. So because of aftershocks especially, do not go back inside a building after the earthquake has took place. Okay, next subject in here, this lecture, we're going to talk about seismology, which is the study of earthquake waves. So study of earthquake waves is called seismology and dates back almost 2,000 years. There's a long history of looking at this earthquake waves. You know, right through Earth history, people have experienced earthquakes. It's a natural Earth process which has happened well before humans were on this planet, or right through Earth history, because it's associated with plate tectonics. So it dates back, but the study of when we started to look at it, it's the seismology dates back almost 2,000 years to China. So this thing on the right, this big bronze urn, and in this case, kind of toads or frogs, bronze toads around it, and some dragons' heads on it. This is the first seismograph, which is a type, basically an instrument to measure the size of earthquakes or the direction of earthquakes. So it's the first earthquake locator device, if you will. So what happens? Yeah, let's go. Sticking with the top part of that slide first, is I've seen these things in museums. They can be, 4 or 5 feet tall. They're huge, incredibly heavy, big metal urns, usually brass, I believe, or bronze. And here you have, in this case, the animals can be changed, but here you have some running around the top of this urn, these dragon heads. And at the bottom, these toads or these frogs with the mouths open. But balanced in between the mouths of the dragons' heads are ball bearings, metal ball bearings. Okay, and they're just kind of balanced there. Inside that urn, you can't see it, there's a big pendulum, a big weighted pendulum. And when an earthquake occurs, let's say in ancient China in this case, as that seismic wave goes through the location wherever this urn is, the ground shaking will cause that pendulum inside that urn to rock back and forth, and it will then, that motion will drop out these ball bearings, and they'll drop into the mouths of the frogs below. So that movement will tell you where the earthquake is, because it'll be moving parallel to the direction where the seismic wave is moving from. But here it'll only give you one of 2 directions. It could tell you the earthquake is over in that direction to the right, or in the opposite direction, let's say to the left, because that's where the ball bearings will drop in to opposite each other there. It won't tell you it's in which direction. So, in ancient dynasty of China, the leader sends out his scouts on horseback to go that direction or that direction and find out what's happened to his town, the towns in either direction, knowing that there has been an earthquake in either direction. So, it was really ingenious, well thought out instrument, essentially, that it was designed 2,000 years ago to locate an earthquake. What we now use, the modern day instruments, are called seismographs, and these are the instruments that record seismic waves. They can record the strength of an earthquake especially, but also we can use them together to, as we'll find out, to calculate or work out the location of an earthquake. So seismographs, they record the movement of the Earth in relation to a stationary mass on a rotating drum or a magnetic tape. So here you can see a rotating drum which is kind of suspended underneath the Earth here, and the instrument will take a reading, which is called a seismogram, and take a reading, in this case with the pendulum here, the pivot will move back and forth, and you'll have that typical zigzag line from when you have ground shaking. So here you can see that the zigzag on the paper, in this case, an old paper one, will show the movement, the ground shaking, and it's kind of calibrated to scale how big that ground shaking is. So that's a seismograph. They measure earthquake ground movement and earthquakes, the energy, and the relative size of that earthquake as well. The amplitude, the movement back and forth of the earthquake. So the amplitude is the full wavelength, wave height of that wave. Types of seismic waves. So there's 2 main types. There's what are called surface waves and then body waves. And as we'll see, we can split body waves into 2 subtypes. But firstly, surface waves. These are the ones that you feel during the earthquake. So these surface waves, this type of seismic wave, they travel along the outer part of the Earth's surface, so at the ground level, and they actually have a complex motion. You might see in textbooks they actually do divide them into what are called love waves and Rayleigh waves, but we're just going to call them surface waves. And they have quite a complex motion. It's kind of a twisting of energy as energy translates through the ground surface. These things cause the destruction, or the greatest destruction. They exhibit the greatest amplitude of that wave as it goes through the Earth, but also the slowest velocity. And this is key. Different seismic waves, different types of seismic waves, travel at different velocities. So these surface waves are actually the slowest ones. So if you've had an earthquake occur 30 miles down the road, that's where the epicenter or the focus is. This is the one that arrives to you. This type of seismic wave is the one that arrives to you last. There's other types we're just about to talk about that arrive first, smaller ones, which you probably won't feel, but they're the ones that get to you first, the body waves. But the surface waves will arrive last, maybe only a few seconds, or maybe a minute even, if the epicenter is a long way away. But they are the ones you feel cause the destruction. Yeah, so just carrying on. So in seismology, to finish this subject, there's body waves, which are the ones these are second type. So we had surface waves. These are ones that come through the ground. So they travel through the Earth's interior, and there's two types based on the mode of travel. There's primary or P waves. These are we just normally just call them P for primary, but also nicely they go with the motions P for push pull. So the compression and expansion. I'll show you this in a diagram what that means. Changing the volume of the intervening material. The key, they travel through all types of states of matter, be it a solid, a liquid, or gas. So they can move, these P waves travel through an ocean, for example. If you have a seabed earthquake, they will travel through that sea or through a lake. And then there's the secondary waves. And these have what's called a shake motion, as if you're shaking a rope, and it translates that energy along. And the motion is at right angles to the direction of travel. I'll show this different types in the next slide. We'll show this in a diagram. But secondary waves, so these are both types of body wave. They're small in terms of energy. You wouldn't actually feel them, but a seismograph will measure them. But you as a person wouldn't feel them. The key thing is secondary waves travel through solids only, and the secondary waves are slower velocity than the P waves. So the key thing to remember is the P waves are the fastest seismic waves. The P waves have the highest velocity. That's key. Second, number two, in terms of velocity, is the S waves. And third, the slowest waves are the surface waves. So the quickest ones are the P waves. They move the fastest. Then it's the S waves that follow on after behind, and then gradually the surface waves trailing behind those. So here to show those different types of motion of the P and S waves. At the top, the P waves, you have this compression pull. So imagine a slinky. Remember, you got these slinkies. You can you go down a staircase. I don't know if you remember those when you were a kid. But here, just a coil spring. The slinky, you're attaching it to one end, in this case of a fixed point on a wall. But if you kind of move it back and forth, you will then translate an energy compression, expansion, will move down that coiled spring. That's exactly how a P wave moves. And you can see on the top right how that can snap overhead wires, etc., and cause cracks in roads. An S wave, imagine you've got a rope fixed at one point, and then you shake it up and down, and you'll see that curved rope, that curve translate from one end to the other end of that rope, and that's exactly how an S wave travels through the Earth's surface. A surface wave, by the way, it's kind of a combination of both. It's kind of a twisting and wrenching as it goes through. So you use these things. The key thing is to use the difference in speed to locate an earthquake. So how do we locate an earthquake? It's all to do with the difference in velocities between a P and S wave. We'll find out. Going back to those key terms, let's remind ourselves, because they'll come back now. The focus, or sometimes called the hypercenter. This is a place within the Earth where the earthquake waves originate. That's where the actual energy comes from. The epicenter, that's the location on the surface, directly above the focus on the surface, on the ground surface. We can put it as a point on the map. The epicenter is located how do we locate this earthquake? We feel an earthquake at a seismograph, or you feel an earthquake. Where did those energies, those waves, where did that energy emanate from? Where did it occur? In the state of California, within China, within whatever country you're in. So the epicenter is located using the difference in velocities of the P and the S waves. So here's a seismogram reading, which is what a seismograph produces. So here it's rotating, this rotating drum. Here's the squiggles when the energy goes through. So the first one, and the vertical lines are each minute. The first one wave to be shown on the seismogram is the P wave, this small oscillation here. So that's the P wave. It's arrived to your location first. Say the epicenter might be 100 miles away. The first wave to get to you is the P wave. Then in this case, 1, 2, 3, 4, 5 minutes later, you have the S wave occur. And then another 3 minutes later, that's when you actually feel it. And it's also on the seismogram, the large surface wave. Okay, so how you locate the epicenter, we'll use what we've just said, as will become apparent. And so what you need, you don't need just one seismograph station, you need 3, or at least 3, but certainly just 3 are needed to locate the epicenter. It's all to do with ways of triangulation, as we'll see. So each station determines the time interval between the arrival of the first P wave and the S wave. So that's calculated at each of the stations, the time interval in minutes. Is it 3 minutes? Is it 4 minutes for each station? And the travel time, what's called a travel time graph, a calibration chart, is used to determine each station's distance to the epicenter. And I'll show you that on the next slide, what that means. So here you have 3 seismogram readings, 3 seismographs, one in India, one in Australia, one in France. They can be on different sides of the planet. So big earthquakes travel right through the Earth's surface, Earth's interior. So here in India, the interval is 1, 2, 3, 4, 5 minutes. It's around 7 minutes in Australia, and I think, if I remember right, it's about 10 or 11 minutes in France in this case. Okay, so you've got those 3 readings. What next? Well, for each of those, you can work out its distance from that seismograph to the epicenter. And what you do there, you take a bit of paper, they have these curves on them, and this is distance along the x-axis and time along the horizontal axis. So, sorry, the vertical axis. And firstly, the S wave curve. So here it shows you after 1,000 kilometers how long it would take. So it's basically the velocity. The S wave is slower. So anyway, for the S wave, let's go back, start again. For the P wave's quicker. So to get 1,000 kilometers, it takes only 2 minutes. If I show you on this chart, so that's this point. The S wave is slower. Imagine the 2 vehicles. The P wave's traveling at 60 miles per hour. It's actually a lot faster than that, but and the S wave is traveling at 40 miles per hour, so a lot slower. So it gradually gets more and more behind the P wave. The distance between the two gets greater, and that's the key. So here, for 1,000 kilometers, the S wave might take you 4 minutes. So wherever your time interval, you've got your seismograph, you can do this in the lab as an exercise. You just take it at the same scale in minutes and take it down to a 5-minute interval, and you slot that in, and there you go, 5 minutes between your P and your S wave for example, the India seismogram. That will tell you, you put that in there, the vertical line, and then you read across down, and it tells you the earthquake took place, the epicenter was 3,500 kilometers away. You do the same for all 3, and that will locate the epicenter, as you'll see. So a circle with a radius equal to the distance you've just got on that time travel chart, to the distance the epicenter is drawn around each station. The point where all 3 circles intersect is the earthquake epicenter. Let's illustrate that. Now it should be apparent. So you've worked out from the PS time interval, the distance to the epicenter, but for each individual seismograph, it could be in any direction. You just know it's 3,500 kilometers away in whichever direction, whatever the distance you've worked out on that graph. You plot your 3 circles. Where they meet, there's only one point where they always all meet, and that is where the epicenter is, and that's how we do it. Computers can do it now, but you can still do it as a paper exercise, and that's where the epicenter is on Earth. So that's how you locate. So if you plot all those epicenters on a global map, you'll see they're located not randomly, but they're distributed especially around the plate boundaries. So like we've learned with volcanoes, remember the Ring of Fire? Here you can see all the way around the Pacific Rim, there's all these red dots show earthquakes, epicenters, and you can see there's a whole ring all the way up the western part of the Americas, near the subduction zones off Chile, etc., and all the way through Central America. And there's earthquakes associated with the San Andreas Fault, then running all the way around the Pacific, etc. So you'll see these earthquake belts, as they're called. So there's a circum-Pacific belt, as it's known, which kind of mirrors the Ring of Fire, and it's also from the collision of the African plate into Europe and India into the rest of Eurasia, the Alpine Himalayan belt. You can see a much wider belt of earthquakes there. But also you see, if you look down the middle of the oceans, you get lines of earthquakes associated with spreading centers, so mid-ocean ridges, where magma is being forced up from the mantle below, and you get partial melting and seafloor spreading. And there is a difference, though, if you look at the details of these earthquakes. The ones around mid-ocean ridges and divergent boundaries are quite shallow, relatively shallow in the Earth's crust, while the ones associated with subduction zones, so as one plate is going subducting deeply underneath another gradually, those earthquakes get deeper and deeper and deeper on basically on the top side of the subducting plate. So you get very deep-rooted earthquakes of a range. The further away you get away from the subduction zone, so inland, those earthquakes can get very, very deep. The foci. Also, there is a few, though, of these red dots in what we call intraplate locations. Some are associated with hotspots, like in Hawaii and Iceland or Yosemite, but also there's a few elsewhere. So in the next slide, we see a map of the US and earthquakes there, and this map shows kind of essentially a hazard map, the amount of damage that could be expected from earthquakes. And you see mostly the dark browns for the major damage are located in California, especially where you'd expect them, associated with the San Andreas Fault and the faults that are associated with there. Also, some that are related to subduction zone earthquakes around Seattle in Washington State. But then there's these ones on the eastern side of the United States where you would maybe you wouldn't expect them, and especially clustered around an area called New Madrid, what's called the New Madrid seismic zone. And historically, there was a very large earthquake that took place at New Madrid. Here it is, sort of in the Mississippi Valley, the western point of it's a juncture of several states, western sort of Kentucky, Tennessee. And back in 1811, December 1811, through into January 1812, there was a series of 3 earthquakes, all of them over 7.0 on the Richter magnitude scale, which is large, which we're just about to learn about the magnitude scale. So they're large, significant earthquakes, well away from a plate boundary, these intraplate settings. So why do they occur there? You know, we kind of learned they're associated with either compression or extension to do with earthquakes, with plate boundaries. Well, what we geologists now know is that if you look deep under the Earth's crust at this point around New Madrid, in very old rock, sort of 600 million years ago, sort of very early life essentially, there was at that point in Earth's history where continental rifting was taking place, and the North American plate, or the North American continent at that point, was about to be wrenched apart. Then, for whatever reason, magma stopped rising from beneath, and the continental rifting kind of stopped at that point there. But there's also now currently some compressional forces going on, and they are basically reactivating those very deeply buried faults and fractures deep under the ground here, and that's why you have sometimes very large earthquakes, and there's still potentially a chance for large earthquakes in the future. So this seismic zone, it actually follows this former initiation of continental rifting, which goes up through the Mississippi Valley, New Madrid, then up to the northeast through along the St. Lawrence River Valley, and the border between the US and Canada. So you do get the key point here is you can have earthquakes in these intraplate regions here. Okay, so next, the final topic on this lecture is how we measure the size of earthquakes. So there's two measurements that describe the size of an earthquake. There's two scales essentially. There's something called intensity, an earthquake's intensity, and the magnitude, earthquake magnitude. So firstly, intensity is a measure of the degree of earthquake shaking at a given location based on the amount of damage. So you assess the size of the earthquake purely based on the structural damage, or just windows kind of broken, a few tiles off the roof, or do you start having buildings collapsing essentially, or is it a complete collapse? So it's a relative scale. So I'll show you the detail on that in a second. It's a measurement very much for management and policy. So you look at an area where an earthquake has struck and you decide how much damage has been done structurally. So therefore, then you can target your resources on the areas with more intense destruction. The magnitude scale, this estimates the amount of energy released at the source of the earthquake. So it's a kind of a scientific measure of the amount of energy released. So to go through each of those scales in a little bit more detail with some examples. So the intensity scale, first of all, its full name is the Modified Mercalli Intensity Scale. It was developed in the US using California buildings as its standard. The drawback of intensity scales is that the destruction may not be as a true measure of the earthquake's actual severity. For example, it's based on California buildings. California buildings are quite robust, high building codes. So you need a very large earthquake to cause major damage. To show you examples of Mercalli intensity scale. So essentially it's a descriptive scale given in Roman numerals from 1 to 12. So 1, not felt except by very few under especially favorable circumstances. 2, felt only by a few persons at rest, especially in the upper floors of buildings. I won't read everyone out. Then let's go through to 4 maybe. During the day, felt indoors by many, outdoors by few. It's a sensation like a heavy truck striking the building. I was actually living in the Washington DC area when there was one a bit like this in 2010, the Virginia earthquake, and that felt somewhat like that. 5, felt by nearly everyone, many awakened. 7, everybody runs outdoors, damage negligible in buildings of good design and construction, slight to moderate in well-built ordinary structures, considerable in poorly built or badly designed structures. So those moderate to large ones is a huge difference in the amount of damage done depending on how well designed those structures are to withstand ground shaking, which is a key. And once people realize that, there's lots of effort goes in now to in earthquake-prone areas to construct buildings to a very high building code, and we'll mention that in the next lecture. Let's go to 9. Damage considerable in specially designed structures, even the specially designed structures get this damage. Second highest one, 11. Few, if any, structures remain standing. Bridges destroyed. Broad fissures in ground. And the strongest of all, damage total. Waves seen on the ground surfaces. They like to show that on all earthquakes in Hollywood movies. But objects thrown upwards into the air. Okay, so that's the descriptive modified Mercalli intensity scale. So when you plot out all those values, you can draw a map with zones of destruction or intensity associated with this. Here, this is a map for the Loma Prieta earthquake of 1989, and the Loma Prieta earthquake was the largest earthquake that has been in recent times in the San Francisco Bay region. It's actually a little bit south near Santa Cruz, south of San Francisco, but it's the largest one in that area. since 1989. All my life they've been talking about when will the next sort of 1906 style big earthquake affect the city itself. Well, it hasn't happened yet, but the likelihood is increasing that we will have a large one with an epicenter actually right near the city of San Francisco at some point. These zones, by the way, the intensity scale is based on questionnaires usually, or people actually going out and surveying damage. So it's you build up this picture straight after the earthquake. You go out to different neighborhoods and ask the locals, questionnaires about the damage. What did it feel like? What did they see? Observations, and also simply taking a physical survey of the damage around a city, for example, or a region. And then you build this sort of map up. Again, very useful for focusing your resources on an area, showing where the most damage took place. Associated with this sort of thing, measuring the size of earthquakes are shake maps. And where a shake map is produced by using high quality seismograph data to show areas of intense shaking. So it's actually if you are in an area which has a very good seismograph network, lots of seismographs, and you can do a very detailed map essentially of literally during the earthquake how much shaking was going on, ground shaking in different locations. So it's useful in the crucial minutes after an earthquake. You can do it instantly now with computers, and you can link to these seismograph recorders, and you can instantly find out where most ground shaking took place. So they can show emergency personnel where the greatest damage likely occurred, and locate areas of possible damaged gas lines and other utilities, importantly. Okay, so finally the magnitude scale. So the magnitude scale originally was called the Richter magnitude scale, concept introduced by Charles Richter way back in 1935. The Richter scale is based on the amplitude of the largest seismic wave recorded. Originally, the largest magnitude recorded on this initial Richter scale was 8.6. Magnitudes less than around 2.0 are generally not felt by humans. Each unit on the Richter scale, each unit of Richter magnitude increase, corresponds to a 10-fold increase in wave amplitude, a sort of logarithmic scale. But also, and maybe more importantly, is a 30-fold, it's actually 32, but that's a 30-fold times energy increase. So every unit you go between, say, let's say a magnitude 6 to a magnitude 7, a magnitude 7 is 30 times more energy released than a magnitude 6. With that in mind, I'll give you a little quiz to think about, and then I'll tell you the answer. So a magnitude 8 earthquake is how many times more powerful than a magnitude 4 earthquake? So it's 4 points on the Richter scale. How many times more powerful? And I said each increase is 30-fold. So think about it, maybe. You might need a calculator. Okay, some people, when I've given this in class, opt for C, and they simply add 30 times plus 30 plus 30 plus 30. But that's not how you do it. You go 30 times 30 times 30 times 30 times 30, and that answer will pop out at 810,000 times more powerful. So it just shows you, illustrates as you go up the Richter magnitude scale, the energy gets hugely increases with each magnitude point. The latest magnitude scales is called the moment magnitude scale. Basically, the Richter scale has been kind of tweaked because the Richter scale doesn't adequately estimate very large earthquakes, the very largest ones. The largest earthquake recorded, it's a Chile earthquake of 1960. That was a 9.5. That's the largest ever recorded. 9.5 in Chile in 1960, 1961 or 1960. 1960, the date's here. Okay, this diagram shows, it's actually a lot of information on here, but it's good information. Firstly, down in the middle column, these numbers, the number of earthquakes per year worldwide. So 1 million, magnitude 2. Remember how normal people can't even feel those. Very minor earthquakes felt by, but number 3, felt by humans maybe. 100,000, etc., and they get less. So the large earthquakes, and I may have mentioned anything over maybe 6.5 is something where you really need to pay attention. There's a lot of damage potentially done depending on where you are. Magnitude 7, around about 18 per year, and then much less. So magnitude 8, remember, 30 times more powerful than magnitude 7, only 1 per year, and magnitude 9, thankfully less than 1 every year. So some notable large earthquakes from history: the Chile earthquake in 1960, the largest one ever; the Anchorage earthquake from Alaska, 9.1, the largest earthquake in North American history, 1964. And the New Madrid earthquake, it was a large earthquake, 1812. Here it's quoted at just over 8 magnitude. The great earthquake of San Francisco, that was around about 7.8 of 1906. The Loma Prieta one, the largest earthquake in the San Francisco Bay region, 1989, that was less than 7, it was a 6.9. If you put the Haitian earthquake more recently of 2010, devastated that's the capital city there of Port-au-Prince. Over 160,000 people died. That was about a 7.0. Other earthquakes like the Japan earthquake of 2011, a 9.2 you could put on there. The 2004 Indonesian earthquake and tsunami, that was about a 9.2. The energy equivalent, so this gives you an idea about the amount of energy being released. So the Hiroshima atomic bomb from World War II, that was, in terms of earthquakes, about a 6.2. Mount St. Helens eruption, largest eruption, right about the same size as the amount of energy released as the San Francisco 1906 earthquake. The largest nuclear explosion, so the largest ever explosion, man-made explosion from the former Soviet Union in the 1950s or 60s, that was around about an 8.0 on the scale. So earthquakes get larger than that, and larger than many even huge historic volcanic eruptions like Krakatoa. Okay, finally, I'm just going to tell you about 2 earthquakes, a story of 2 earthquakes, just to illustrate hopefully the difference between intensity and the magnitude, the energy increase. So the intensity scale measures damage, not magnitude. So kind of bear that in mind. The Mercalli intensity scale measures the actual amount of damage, not the actual size of the physical size of the earthquake. 2 earthquakes, tale of 2 earthquakes. Charles Dickens here. So Northridge, California, 1994, magnitude 6.7. So it struck just north of Los Angeles. The Hector Mine earthquake of 1999, further south in California, that was a magnitude a bit larger, 7.1. Okay, so first the Northridge earthquake happened just to the northwest of Los Angeles. The star here shows the epicenter. Struck in January 1994, 6.7 magnitude. 60 people died from this. More than 7,000 injured. 20,000 were made homeless. More than 40,000 buildings damaged in sort of the northwest suburbs of Los Angeles and into the counties just north of there. It occurred when there was displacement along, a movement along a actually buried fault. You couldn't see the fault. It was along what's called the Santa Monica Thrust Fault. There's compression occurring. So this is a thrust fault, a type of reverse fault occurring. Northridge just above there. Pictures of some of the damage from the Northridge earthquake. There was a lot of structural damage, building collapse, freeway collapse here. Here's the California State University parking lot collapsed, etc. So this is why you had the so many buildings collapse. The numbers, about 60 deaths, unfortunately, due to this. 7,000 people injured. Okay, this is the intensity map, earthquake intensity that was produced straight afterwards, and you can see in the middle the redder colors, or here on the left you can see from on the intensity number scale. Here would be 9 would be the strongest, so there's pockets of 9 right in the middle, and then 8. And it gets less intensity as you'd expect further away from the epicenter, which is in the middle, and so the amount of damage gets less with distance. But there is note from here though, when you look at this carefully, there's these pockets of, again, to the south of 7 and sorry, of 8. It rises again. You see these little red areas here. So, in class I'd ask you what's your thoughts? Why do you think that might happen? Why is there more damage in these locations. If you look at the map, there's Los Angeles, kind of downtown Los Angeles. These are kind of inner city suburbs just north of Los Angeles. So these are basically the poor neighborhoods. So these houses are structurally not very well built, and no one's had the money to go back in and what we call seismically retrofit them, make strength in them. So that's why there was actually more damage in these areas. Okay, the second earthquake of the two is a hectomine earthquake of later in 1999, a larger earthquake, 7.1. The event was located in remote, sparsely populated part of the Mojave Desert, though, in Southern California, approximately 32 miles north of Joshua Tree. And here's the seismograph going crazy after this very large earthquake. 7.1 is a significant earthquake. And here is a photo of about the only known damage from the hectomine earthquake. So you can see these big cracks in the ground out in the Mojave Desert, and therefore on the intensity scale there'd be about 0 or 1. So it just gives you an idea, hopefully, that you need structures there to be damaged to be on the intensity scale. It's all about damage. It's not actually about the size of the earthquake. But this hectomine earthquake, the actual ground shaking, if you stood there, you'd be, you'd feel it an awful lot more than you would at the Northridge. But just bear in mind, like I say, the intensity is all about the actual damage. Okay, so that's it for this Earthquakes Part 1 lecture. Next of the 2 lectures, we'll be looking at going through the different types of damage, including building collapse, fires, landslides, something called liquefaction. We'll be talking about whether or not we can forecast earthquakes and about mitigation efforts, what we can do to reduce the risk. All right, guys, thank you for joining me this time, and I'll see you again soon. Thanks.